So what we're looking at is how we can find the line brought about by the intersection of two planes. So if we have, for example, plane 1 and plane 2, provided that these planes are neither coincident nor parallel, what you're going to find is that they're going to cut each other in such a way that there's a line defined between the two of them. So if we have a look on the screen over here, you can see that there are two planes, and you can see that there's clearly a line defined by how they cut one another. What we're going to do is we are going to determine how we can find the line that defines the intersection of two planes. Now, this method I'm going to show you is a lot easier than the method I've been using the last few years, which is nice. So, we've got two planes as shown on the board. Plane 1 is x plus y plus z equals minus 1. Plane 2 is x plus 2y plus 3z equals minus 4. What we want to do is we want to find the equation of the line that describes the cut between the two planes. Now, this can be done in two steps. First step allows us to see if it can even be done, and then the second step basically reveals to us the actual line. So first thing we're going to do here is we ask ourselves, determine the direction of the would-be line. So, what we're going to do is we're going to get the two normals of the two lines we have. The first normal, what is that going to be, please, Mad Dog?
1, 1, 1.
And then Lenny, what's the second normal?
1, 2, 3.
Whoops. 1, 2, 3. Now, the line that is going to run, the line that's going to run between the intersection of the two planes happens to be perpendicular to the two normals defined by the plane. So how do you think we're going to find that direction of the line?
Cross product.
Bingo.
Oh my god, Nick.
Do you remember what the cross product is, Nick?
Right. The vector, the big X, and the vector. It's every lesson. Yeah.
Whenever I ask a question, the answer is either going to be dot product or cross product.
The orthogonality.
Okay, so if we compute the cross product of these two vectors, we can put it in our calculator, and what we're going to discover is that we get the value I don't think I actually calculated it here. Brad? No, I just wrote that I would calculate it, but I didn't actually calculate it.
1, negative 2, and 1.
1, negative 2,
And 1.
and 1. Okay, and this brings us to our first point of interest. If we try and calculate the cross product, well actually before we even calculate the cross product, we have to think, what if our two normal vectors here are scalar multiples of one another? What would that suggest?
Intersecting at every point?
Potentially parallel or
Not
coincident. If they're either parallel or coincident, is there any point going past this point here? No, because they're never going to intersect. So the first step is determine the direction of the would-be line. If you discover that your two normal vectors are scalar multiples of one another, stop, because you're wasting your time. There will be no intersection. Or there'll be infinitely many intersections. In either case, it won't be a line, it will be a plane, or there'll be nothing at all. So this is first step. This is the direction of the line that we're going to find. Next step is find a point
If that's got a 5-star job.
of intersection. Now, to find the point of intersection, all we need to do is we simply state our equations, but where there's going to be a catch. We're going to let z equal 0. It doesn't matter what value of z you choose, I just choose 0 because it makes the import easier. So we're going to go equation 1, which is x plus y equals minus 1. And then our second equation is going to be x plus 2y equals minus 4. This is 1, this is 2. Now, remember, we're looking at a reality where two realities merge together. So what do you think we're going to go for if we're looking for the reality where two realities merge together? Simultaneous equations, it's easier to subtract. So we subtract the two equations to bring the system together. This is going to be 0 x's. This is going to be minus 1y, and this is going to be 3. Solving this, when z is 0, y is minus 3. Putting it all together, we're going to get x plus minus 3 equals, so that's for the first system here, negative 1. So x is going to be plus 2. Hence, we have a position in space, we have a direction through space. Do we have enough information to determine our line of intersection, Rowan?
Not yet.
Of course we do.
Yes, you did.
Line of intersection L1, or we'll call it Li, is going to be, our position is 2, minus 3, 0, plus, we'll pick lambda. Actually, we always pick lambda, let's pick mu. That's an ugly mu. Our direction is going to be 1, negative 2, 1. Done. Next question is, did we get it right? Let's find out.
Verify with GeoGebra.
GeoGebra, my favourite tool in this topic, because it allows me to check if I'm actually doing the calculations properly or not.
Or you just have the handy tool.
No, Chad gets it wrong, and it's very confident when it gets it wrong as well.
No, I use the wolf from Alpha GPT.
Wolf from Alpha is pretty good.
But like the GPT version.
It's got a GPT.
Yeah. So when you ask it to graph it, just graphs it.
What does GPT stand for?
I don't know.
Growth production.
It's just a brand name. Yeah. You can ask it to like do lots of things. Or like just grab the graph from the
Yeah, it's from, I used to use it a lot.
Not anymore.
Not since chat.
Not since chat.
No, to be honest, I'm less reliant on it. So it's actually a really great tool. If I was learning something new, I'd use it a lot. Okay, so there's our cross product.
Which one?
Our point is one of them. Our point of interest was 2 minus 3, 1. Okay, those are our normals. This is our direction of the vector, and this is our point of interest. You can see the point, it's not lying on the intersection.
2 minus like 1, 1 or 0. It's 0 instead of 1.
There we go. Yes, it's on. No? Oh, it's not.
It's only lying on one of the planes.
Yeah. 2 minus 3 is 0.
Have I made a mistake?
X.
Or keep going. And we'll troubleshoot it in a second. So it's slightly off. That tells me that I made a mistake somewhere.
So your simultaneous equation, I don't know actually.
The problem is
I'm
simultaneous.
just yapping to be honest.
In equation
Oh
one,
yeah, you've got
is it
x
x plus y plus x?
Whereabouts is it?
in GeoGebra.
Yeah.
Oh, GeoGebra. Whereabouts is it? X plus
Equation
y
one.
minus x. Okay,
Oh, there we go.
there we go. Is that on?
Yep.
Yeah, that's on. Nice. Okay, so do we see what's happened there, boys?
Yes.
So the first thing you do is try and do the cross product. If you discover that your two planes are scaled, the direction of your two planes is a scalar multiples of one another, you're either in a situation where they're coincident, so they're perfectly on top of each other, in which case you only have a singular plane, or you're in a situation where they're parallel or there's no line of intersection. In fact, in either case, there is no line of intersection. Second situation that you look for is you're looking for the point that lies upon the intersection. Simply set one of the variables to whatever you want it to be, and then calculate the other two out of it. Remember, you have, what was it? If you constrain one variable to a value, then you'll have two unknowns with two equations with two unknowns, so you'll be able to solve the point. Seem cool?
Interesting.
The other thing you can do as well is you can skip the first step and you can just set z to t and solve simultaneously from there. That's the method I used to use last year, but I find this one's a little bit simpler. Simple? Legendary. So